Okay. Now we have seen how to find the Fourier transform for periodic signals. To say it again, we find the Fourier series coefficients and we scale them by 2 pi and insert impulses. Now I'm going to show you quite an interesting example. This example is particularly fascinating for me, because when I first saw it in my third year, when I was an undergraduate like you, and the professor was explaining this and giving us this example, and I was totally surprised. And I will try to explain what is the surprising situation here. The example is as follows. By the way, from the exam, I can see that some of you guys had difficulty in understanding what this kind of a signal means. Because there was a convolution question in the exam. This signal is a periodic impulse train. It is also known as an impulse train. Okay? Periodic impulses. How much are they separated? What is the separation between two impulses from this formula? Capital T. They are separated by capital T. The first one is at 0, then at capital T, at 2 capital T, 3 capital T, to the left hand side at minus capital T, minus 2 capital T, etc. So it's a periodic impulse train, and the convolution was related with this one. Some of you guys just considered this. By the way, in the exam question, it was the capital T was 5. And some of you guys just tried to convolve the shape, the triangular shape, with only one impulse at k times 5. And k times 5 is a number, you assume, and you are convolving that. There is no k times 5 or anything like that. These are many impulses. And k is from minus infinity to infinity. It's a summation. It's not a single k. Okay? So, this is periodic. Okay, with omega 0 is equal to 2 pi over capital T. That is, these are the Fourier series, the fundamental frequency, and therefore from periodicity we have the Fourier series coefficients, AKs. Although we found the Fourier series coefficients before in our notes, I'm going to repeat it here. The formula for the Fourier series coefficients. And within one period of integral, 1 over t times within one period of integral, we have x of t, and within this period, from minus t over 2 to plus t over 2, there is only one impulse in between. That is delta t. That one fits into the integral range. E to the minus j times omega 0 t dt. K is also here. E to the jk omega 0 t dt. And delta t is, you remember the trick, it's non-zero at t is equal to 0 only, which makes this thing at t is equal to 0, e to the minus j omega 0 kt. What is that at t is equal to 0? E to the 0. So this thing becomes 1. E to the 0 is 1. And therefore we have 1 over t, integral from minus t over 2 to t over 2, delta t times 1 dt, which is the area under delta t, and that is 1, and we have a 1 over t in the scale, so this is equal to 1 over t for all k, for all integer k. So the Fourier series coefficients are always 1 over capital T. It doesn't depend on k. AK is equal to 1 over capital T. Always. What are the corresponding frequencies for an AK? The corresponding frequencies are omega is equal to k times omega 0, or k times 2 pi over capital T, that was omega 0. So how am I going to draw this? Its plot is fairly simple. On the frequency axis, well, how am I gonna get rid of them? Okay. We have to have a lot of impulses, in fact infinitely many impulses, because AKs exist for k from minus infinity to plus infinity. We have infinitely many impulses. The first impulse is at omega is equal to 0 times omega 0, which is the center. And what is the magnitude of that impulse? It is 2 pi times A0. A0 is 1 over t. They are all 1 over t anyway. So 2 pi over capital T is the magnitude at 0. And then where's the other one? The other one is, let's say, here. At k is equal to 1, that is 2 pi over capital T. And the magnitude is the same, 2 pi over capital T. At 2 times 2 pi over capital T, the magnitude is again 2 pi over capital T. We have an impulse here, another impulse here. To the right and to the left, we have a lot of impulses. Infinitely many impulses. So, how can we express this thing? X of capital X of j omega. Can we write it? Let's write the formula for these impulses. How can we say? First, we need to put the scale, which is 2 pi over capital T, the magnitude of the impulses. And since it's a periodic impulse train, we are going to write it in the formula of a summation, in the form of a summation from minus infinity to infinity, delta omega minus k times 2 pi over capital T, or omega 0. So this, I claim that this is the Fourier transform. Do you agree with it? First of all, okay. This is the Fourier transform, and there's no trick or anything about that. Now, let's put it in a box and try to find the Fourier transform in an alternative way. Let's think of the Fourier transform of delta t minus capital T, delta t minus 2 capital T, etc. What are the Fourier transforms of each of these things? The Fourier transforms I'm going to write at the right hand side like this, one by one. And since the impulse train is a combination of these impulses, the Fourier transform from linearity will be a combination of the Fourier transforms at the right hand side. That's also an alternative way of attacking the same problem. And we know that the Fourier transform of delta t is 1. We just found it. It was the first example today. The Fourier transform of delta t minus capital T will impose a shift in the exponent, in the integral. And you may just try to find it by yourselves if you wish, but it will be e to the minus j omega capital T. That will be the Fourier transform. And the Fourier transform of the third term will be e to the minus j omega 2 capital T. And it's going to go on like that. And I'm saying that the summation here is k from minus infinity to infinity delta t minus k times t, which is the impulse train that we have. And when we sum up these complex exponentials, the combination will be equal to the summation of, again, let's say k from minus infinity to infinity, e to the minus j k omega capital T, 2 capital T, 3 capital T, or minus 2 capital T, etc. Okay, so this summation is therefore the Fourier transform of the left hand side, and I'm going to put it in another box, and I'm claiming that it is also equal to the Fourier transform, which is correct. Okay, I'm not giving you any tricks or anything. It's true, it's correct. What is fascinating what was fascinating for me, and it is still quite fascinating, is that this box expression is the same as the previous box expression because they both correspond to the Fourier transform of the impulse train. So this is equal to, what was it previously? 2 pi over capital T summation k from minus infinity to infinity delta omega minus 2 pi k over capital T, or k times 2 pi over capital T. It's the same. Yeah, that's it. So this is quite surprising, and I don't know if you can grasp the surprise here. What is so surprising? What's the big deal of this equation? The top one is equal to the bottom one. The top one is a summation of exponentials, complex exponentials, which are sinusoids, basically. Okay. And the bottom one, on the other hand, is an impulse train. This one, this shape. So I'm summing up a lot of sinusoids. Sorry, this expression, summing up a lot of complex sinusoids, adding them up, and I'm getting an impulse train. Isn't it interesting? How can summation of sinusoids converge to an impulse train? It seems quite impossible, doesn't it? Because sinusoids are continuous entities, smooth, continuous, even differentiable, and we come up with discontinuous impulses as their summation. Not only one, but infinitely many impulses we come up with. So that was something surprising for me. By the way, if I ask you the Fourier transform of an impulse train, and if you give me the top answer and say that, sir, the Fourier transform is that, then you get 10 points out of 10 points. And if you say this is the Fourier transform, you again get 10 points because they are the same. But of course, if the question will follow with further analysis, one of them may be more useful than the other one. And you have to continue with one of them, whichever more suitable for the rest of the question, part B, part C of the question. Well, anyway, so this is the final example of periodic signals Fourier transforms. So for the periodic signals, we first evaluate a case, and then we multiply them by 2 pi and insert impulses. And this last box is how we get it. From now on, as I said, as I promised in the previous hour, we will continue with the properties, or let's open a new page. The Fourier transform properties. This is continuous time Fourier transform properties, of course, because that's the chapter. And these properties will help us solve Fourier transform questions. We already found the Fourier transforms of some very basic things. Some examples we have seen. Some of the examples we didn't cover here, but they are available in the book. And in the book, if you inspect the chapter, you will see that there is a table of typical transform pairs. What are they? The typical transform pairs. For example, the Fourier transform of the impulse is 1. It's in the table. The Fourier transform of a cosine is 2 impulses. The Fourier transform of a rectangular shape is a sink. The Fourier transform of a sink is a rectangular shape. The Fourier transform of a complex exponential is just 1 impulse, etc. So you will see a lot of pairs. Not many, but I mean a full table, a table full of pairs. Now you have to photocopy that and keep it with you all the time, and you have to bring them to the exam as well. The typical transforms. It's in your pocket. It's there. And then you have another list of, this time, properties, and we are going to cover those properties. It will be tabulated as well. You will also photocopy and cut it and have those 2 tables table of typical transforms, and table of properties. Starting from the typical transforms and using the properties, combining those information will enable you to solve a lot of problems. Most of the problems, in fact, you will solve by using properties. And what are those properties? We will cover them one by one, and then we will see examples about how you can really use it. The first property is quite an obvious one, that is linearity. The property says that if the Fourier transform of x of t is x of j omega, and the Fourier transform of y of t is y of j omega, and by the way, these double-sided arrows usually correspond to the Fourier transform pair. So xt and xj omega form a Fourier transform pair. Then, if you say z of t is equal to a times y of t plus b times, a times x of t plus b times y of t, then the Fourier transform z of j omega, capital Z of j omega, will be equal to a times x of j omega plus b times y of j omega. So the Fourier transforms are also combined. Or if you scale the signal, then the Fourier transform is scaled by the same value. That is the linearity property. The second property is the time shift property. Says the following: if x of t has a Fourier transform of x of j omega, then the shifted version of this, by the way, in the previous minute, I just used this property without indicating that it's a property. The time shift will impose an extra complex exponential like this in the Fourier domain, x of j omega. Okay, this is minus. And the properties, most of the properties, although they are tabulated, they are trivial. I mean, when I ask you just to prove it, their proofs are very simple. They don't even require a proof. For example, we can continue with this one if you wish. How can we prove this property? How can we say that if the time signal is shifted by an amount of t0 to the right or to the left, the Fourier transform contains just one extra complex exponential. Let's do it like this. Suppose x of t, x of j omega is equal to integral from minus infinity to infinity x of t e to the minus j omega t dt is the Fourier transform, as we see. Then what can we say about y of t is equal to x of t minus t0? What's the Fourier transform of y of t? What is y of j omega? Y of j omega will be equal to, from minus infinity to infinity, y of t is here, which is x of t minus t0 e to the minus j omega t dt. That's by definition. Do you agree with this? And then we say that t prime is equal to t minus t0. Therefore, t is equal to t prime plus t0. That is the change of variable. Instead of t, I will put t prime plus t0. Let's put it. I'm going to write x of t here. Let's not write the boundaries. X of t e to the minus j omega in parentheses. Instead of t, I'm going to write t prime plus t0. And here, I'm going to open a parenthesis of d t prime plus t0. Okay? This is t prime 2, x of t prime. Now, what can we say about the integration limit first of all? If t is from minus infinity to infinity, where is t prime from to? It is also from minus infinity to plus infinity, because by shifting by an amount of finite t0, minus infinity will still be minus infinity and plus infinity will still be plus infinity. Plus infinity plus t0 is infinity, in other words. So from minus infinity to infinity, x of t prime e to the minus j omega t0 e to the minus j omega t prime, and I'm going to write here dt prime, not dt prime plus t0, because t0 is a constant and its differential will not be affecting the differential dt prime. In other words, dt plus 3 is dt. And this one is independent from t prime, therefore can be taken out of the integral e to the minus j omega t0 from minus infinity to infinity x of t prime e to the minus j omega t prime dt prime, and by definition this part is equal to x of j omega, and that is equal to y of j omega. So what is y of j omega? It is e to the j omega e to the minus j omega t0 times x of j omega, which is what the property says. If you shift by an amount of t0, the Fourier transform is multiplied by e to the minus j omega t0. You can expect it's quite trivially the exponential will be shifted by t0, and that shifted by t0 exponential term will go out of the integration from here. It will go out of the integration and it will stay here, e to the minus j omega t0 times the same Fourier transform that we have already. So that is the time shifting, and we used it in the previous question, by the way. It was here. Since delta t's Fourier transform is 1, delta t minus capital T's Fourier transform is e to the minus j omega capital T times 1, the previous Fourier transform. That's what it is. If it is delta t minus 2t, then it is e to the minus j omega 2t times 1. That's the shifting property that we have already used in the previous example. So using these two properties, the linearity and time shift property, now we are, for instance, it's just an example, now we are able to solve or evaluate the Fourier transform of this question without too much effort. Otherwise it will require a lot of effort. The signal I'm going to draw is like this. One, two, three, four. Let's say 5 is here. This is 0. This is 1, and this point is 1.5, and that is x of t. So it's not a rectangular box, but it's a combination of two rectangular boxes or three rectangular boxes, whichever you may prefer. And it is not symmetric around the origin, but it is shifted towards right. The sinc Fourier transform example was a rectangular box inside the origin, around the origin. Okay? This is not around the origin, it is at the right hand side. In fact, it's around t is equal to 2.5. So how can you find the Fourier transform of this one? For that, all you need to say is it's a combination of this rectangle, which is well, we can give a name to that if you wish, and this rectangle from 1 to 4 and from 2 to 3 the peak is 0.5 here, the peak is 1 here on the same time axis, right? If you combine the later two rectangles, the top figure will be obtained. And then we can proceed like this. Suppose that it's not it's not starting from 1 and going up to 4, but let's think that the origin is here, that I have drawn with red. Then this point will be 0, this will be 0.5, and this 4 will correspond to 1.5, and this will be minus 1.5, as I have indicated by red. Okay? So I'm drawing the shifted version of these things to the left. And I'm doing the same for this one as well. This point will be 0.5 and this point will be at minus 0.5. The red ones, I'm gonna call this one, the red one is x1 of t. This one is x2 of t. Okay? The around origin versions. And I'm going to write x of t to be equal to x1 of t minus 2.5 plus x2 of t minus 2.5. Because x1 of t and x2 of t are around the origin, and the original black signals are just 2.5 shifted versions of them towards the right. And when I combine them, I get my original x of t at the top. This x1 of t, okay, I'm not going to write it like that. x1 of t has a Fourier transform x1 of j omega, which is equal to sine omega over 2 over omega. This thing is the Fourier transform of this rectangular shape from minus 1 over 2 to plus 1 over 2 and scaled by 1 over 2, because the peak is not 1, it is 1 over 2. So originally it should be 2 times sine omega over 2 over omega, but since the magnitude is not 1 but it's 1 over 2, that 2 times thing is cancelled and we get sine omega over 2 over omega. This is the Fourier transform of the first term. The Fourier transform of the second term, x2 of t, Fourier transform corresponding to x2 of j omega, is 2 sine 3 omega over 2 divided by omega. And you can extract this sinc information or the sinc equations from the tables, because you should be given the Fourier transform, the sinc Fourier transform of a normal rectangular shape from minus t1 to plus t1. You already have it in your notes. It's in your notes. Just look at the notes and put t1 is equal to 1 over 2 and you will get this. Put t1 is equal to 3 over 2 and you will get this. As simple as that. Now we have to use one extra thing, because it's not enough to put x1 of t plus x2 of t. The combination must be shifted towards right by an amount of 2.5. t0 is equal to 2.5, and that would make x of j omega is equal to e to the minus j omega t0. You remember the shift was e to the minus j omega t0. What is t0 here? 2.5. Okay, that's it. And I'm opening a big parenthesis because this amount of shift is valid for both x1 and x2. They shift the same. So I'm going to combine these two signs, sinc expressions, sine omega over 2 plus 2 sine 3 omega over 2 over omega. Okay, finished. This, I say, is the Fourier transform of the very top shape here at the top. It may be simplified a bit further, I don't know, and I don't care. I'm just trying to illustrate how to attack such problems. You just need to express your signal in terms of shifts and combinations of some known signals. And the known signal for our case is a rectangular shape in the center, because you know the Fourier transform of that. And then you're just scaling it, the magnitude of it, or scaling it horizontally, and then shifting it, combining them, etc., to come up with the question shape. So whatever shifting or scaling you do in time or scale, you do the corresponding Fourier transform property, you apply the properties, and combine the result. And there it is. And that's how you find the Fourier transform for the given question. Alright? It's not an example, I'm sorry about that. It's now a third property, that is conjugation and symmetry. And what do we mean by that? It means that if x of t has a Fourier transform of x of j omega, then first let's think of the conjugate. The conjugate of x of t will have the Fourier transform x conjugate of minus j omega. That is a property. And that property is not a God-given property. It's very simple. Using, again, the formula of the Fourier transform or the inverse Fourier transform, just put it in. Say that x of j omega is equal to the integral of x of t e to the minus j omega t dt. Then take the conjugate of both sides of the equation and try to come up with the Fourier transform of this one. And you will see that the Fourier transform of that will require both the conjugation of the whole Fourier transform expression, and then further negation of omega to make it capital X of minus j omega. Now, so it's easy to prove this, but its implications and its meaning is a little bit more important for us. For instance, if x of t is a real signal, then x conjugate of t will also be real, obviously, because there's no imaginary part, therefore there's no conjugation. So x conjugate of t will be equal to x of t. These two will be equal for a real signal, isn't it? Because you don't have any imaginary part. For a real signal, by conjugating, you don't change anything. You come with the same. You come up with the same signal. These two are the same for real signals. Which means that for the Fourier transform of real signals, these two must be the same. Or you can write it like this. If x of t is real, then x conjugate of j omega will be equal to x of minus j omega. What did I do here? I'm saying that the top two things are the same, means that one, because x of j omega is equal to x conjugate of minus j omega. Let's conjugate both sides. Then x conjugate of j omega will be equal to x conjugate of minus j omega, and x conjugate is x itself. Which means x conjugate of j omega is equal to x of minus j omega. That is a property for the Fourier transform of real signals. And that is something that you have to be extremely careful about. You have to be very, very careful about this. When I ask you, what is the Fourier transform of this signal? And you say that the Fourier transform x of j omega is this expression. And you put it in a box. That is the Fourier transform. Now, suppose that the time signal that I gave you is a real signal. And you say that this is the Fourier transform. Does it have this property? Does it obey this property? You have to check. And for that, let's, just for illustration purposes, let's go to the first Fourier transform example, which was this. X of t is equal to e to the minus at u of t. Is it a real signal? Of course. And what did we find as the Fourier transform of that? We found this. X of j omega is equal to 1 over a plus j omega. Now, using this, is x conjugate of j omega equal to x of minus j omega? Yes, because when you conjugate this, the conjugate of this one is 1 over a minus j omega. That's the conjugate. And x of minus j omega is just replace j omega by minus j omega, which is again 1 over a minus j omega. So they are the same. That's a verification of your result. Your result must always satisfy that property. If that property is not satisfied in your answer for a real signal's Fourier transform, then it means you did something wrong. Okay? This is a very important Fourier transform property. And it has further implications as well, like this. Even part of x of t, what would it correspond to in the Fourier transform? By the way, when I asked this thing in the examination, some of the students asked the assistants the meaning of this. They even asked whether it means expected value or something like that. It's the even part. And what is the even part? The even part is the symmetric around the origin portion of the same signal. What are even signals? A typical example is the cosine. Cosine is an even signal, symmetric around origin, which means x of t is equal to x of minus t. When you flip it around, you come up with the same signal. The rectangular box shape around the origin is an even signal, for example. Okay? And every signal has an even and an odd part. By combining the even and the odd parts, you can construct any signal, including this signal, by the way. And it may be a good idea, if you don't really understand it, just to try to find the even part of this xt and the odd part of it. Let's open a parenthesis and see an example, an easier one, because that's a complicated shape. What is the even part? If this is x of t, what's the even part of this x of t? Can you draw it? And what is the odd part, therefore? Because whenever you draw the even part, you have to draw the odd part of x of t. 2. You have to draw it 2. The even part is this, from 1 to 2, from minus 1 to minus 2. As you see, it's a symmetric signal, and that signal is the even part, and the odd part is this, minus 0.5 and 0.5, 1, 2, minus 1, minus 2. Because when you combine the even and the odd part, if you add these two signals, you come up with that. Do you agree? And this is completely anti-symmetric. It's an odd signal, the last one. This one is completely symmetric, therefore it's an even signal. So when you take the even part of a signal, which means a mapping from here to here, from x of t to even part of x of t, what would the Fourier transform of it be? How do we translate the Fourier transform? Do you remember the Fourier series coefficients or the Fourier transform of cosine? What were they? 1 over 2 and 1 over 2, which are real and symmetric. For all symmetric and real signals, their Fourier transforms are always real and symmetric. So what we get as a Fourier transform of it is the real part of x of j omega. If x of j omega is a complex function, a complex signal, then its real part will correspond to the Fourier transform of the even part of x of t, and the odd part of x of t will have the Fourier transform of j times imaginary part of the Fourier transform x of j omega. For example, what was the Fourier series coefficients of a sine? It was 1 over 2j and minus 1 over 2j. Remember that? They are the imaginary part. They are purely imaginary. There is no real part of that. So for symmetric signals, the Fourier transform is totally real without anything imaginary. And for the antisymmetric, the odd functions, the Fourier transform is always purely imaginary. There is nothing real, no real part. It will be 1 over 2j. It will be minus 1 over 2j, like sine. There is no 1 plus j or a plus b times j. It will be only b times j, purely imaginary. And for the symmetrics, like the cosine, it will be 1 over 2 and 1 over 2, which are totally real, without anything imaginary. So the even part will have the real part. This can sometimes be used in some properties. Okay. In some examples, this property may be useful, and our example is this. I'm just going to write it. I will continue tomorrow without much elaboration, but you may start thinking about that. E to the minus a absolute value t. This signal is quite similar to e to the minus at u of t. E to the minus at u of t was a signal which was 0, and then at 0 it goes to 1 and then starts decaying. Remember that? The first example. Now this one at the right hand side is like that. For t greater than 0, it is this. But for t less than 0, it is this time the other way around, decaying exponentially. So it behaves like this. Okay? At t is equal to 0, it is 1, and then it is decaying at both sides. So this thing, unlike the first example, is totally symmetric. And therefore, we will expect its Fourier transform to be real, without any imaginary parts. But if you remember the first example that we covered, the Fourier transform was 1 over a plus j omega, which was complex, because there was a j. But this one, the Fourier transform will not contain any j's. It will be totally real. And in fact, it will be 2a over a squared plus omega squared. But we are not going to do that today. We stop at this point. Tomorrow we will start with this example and see why this Fourier transform is real.